In this video, we're going to talk about finding inverse functions. Simply put, that the inverse functions are switching of the x and y. So what I want you to do first, using the same pattern or the same worksheet that you have, is I want you to go and create a table of every single x and y for each of the functions. So when we had that one that you were given, now what happens if I switch the x and y in this? So I have 0, -8, 2, -2, and 8, 4. So I'm switching the x and y's on each. So I'm going to graph the 0, -8, 2, -2, and 8, 4. And then I'm going to go ahead and connect the dots and graph. And that should be the inverse of that particular graph. So the way we label it is by calling, if I were to call this graph f of x, then we call this one the f -1 of x. So what I want you to do first is to go through each of these graphs, switch the x and y's, and create your inverse for each one. So here are the first 4 examples of the graphs, and the red charts or the red tables are the inverses. If you notice again that every time it's just simply the switching of the x and the y. The other thing I want to talk to you about is the notation. So if I look at notation, for example, f of x is here, this is f -1. So if I were to, example, call this g of x, we say that this is the inverse of g by g -1 of x. So it doesn't mean we're raising it to the -1. Again, if this was h of x, this is going to be the h, the -1 of x. It simply means they're related to each other. That h is not very clear. So then I have k of x. So this is going to be k -1 of x. And what we also have to notice is that they look like they're kind of mirrored along a particular line, and that's true. This is mirrored along what's called the y is equal to x line. So let me put that in for each of the graphs. So here's all ones with the y is equal to x line drawn, and if we notice, every time we're equidistant from the between the inverse and the y is equal to x line and the original graph and the y is equal to x line. And if we're not sure how to count it, basically what I do is I notice that my y is equal to x line is going from corner to corner, so my my distances are also going to be counted corner to corner. So let me show you what I'm talking about. Let me do a different color here. So as I'm doing this, if I wanted to say, for example, this point here, as I'm going, I notice going corner to corner, it's 1 corner, 2 corners. I'll draw that a little bit better. So let me do that again. So we go here, it's 1 corner, 2 corners. So then also from here, I also can cross 1 corner, 2 corners, and there I am. Any point can be done that way. So 1 corner, 2 corners, here I am. Forgive me, my things are off a little bit. 1 corner, 2 corners. So every distance can be measured. Even this little one here. So like here, this is only half a square, so it's only half a square here. And I think I got the point off just a little bit. But the point is that it's again the same distance going back and forth. So every single one of these will be, here's a good example, half a square off, half a square off. This one is 1½ squares. So this one is also 1½ squares. So what we're going to do is we're going to go down to the next one, and we're going to see if we can't sketch it or do it by, some people like doing it by visually sketching it, some people like doing it by switching the points. So the first thing you're going to do is put in your y is equal to x line, and then try it again. So again, I can take, looking at one of my points here, I can switch the points. I can find the inverse by switching the points here. So for example, this point is -2, 1. So if I wanted to find the inverse, it would be, on my table, it would be 1, -2. Or I could look at here and say I am 1½ from that line, and I can go 1/2, then 1 from that line, and I land on the very same place. So whether you feel like doing it by points, or whether you feel about like visually looking at a reflection across the y is equal to x line, you can get the same way. So quiz yourself and do the other ones. So hopefully these were the answers you got for the next two. And again, it's a little bit harder to see sometimes because we, for me anyways, visualizing the reflection of the y is equal to x line is kind of difficult. So I usually stick with the switching of the x and y tables. But if we go to the next one, let's look at these two graphs. So draw the y is equal to x line, and then find the inverse of that particular line. So here's the y is equal to x line, and here's the inverse. But let's talk about what we're going to do if we don't necessarily have a graph to look at. How do we find the inverse algebraically? Well, this is my original f of x, and this is actually going through the center, through the origin, and having a slope of 1/2. So this is the graph y is equal to 1/2 x. But remember, the definition of inverse is we switch the x and y. Well, let's do that then. Let's take and find the inverse of this particular one, and we're going to switch the x and y. So f of x was y, so we're going to make that x is equal to 1/2 y. So if I get y by itself, I get y is equal to 2x. And to keep with the notation, we have negative f to the negative 1 of x is equal to 2x. And that's in fact what it is. We still go through the origin, but we go over 1, up 2 and over 1, up 2 and over 1. So let's look at the next one. We'll call this one h of x. This was my original line. And when I look at this graph, this is has a slope, I'm going to write it down here, of a negative 1/4 x, and then it's going through the y-intercept at 5. Well, in order to find the find the inverse, we are going to switch the x and y. So instead of h of x, or y is equal to this negative 1/4 x plus 5, now I'm going to switch them. So we are going to do x is equal to negative 1/4 y plus 5. So subtracting 5 from both sides, we've got x minus 5 is equal to negative 1/4 y. And then isolating y, we've got y is equal to negative 4x plus 20. So using the same thing, if this was h of x, the same notation we're going to do h to negative 1 of x is equal to negative 4x plus 20, which we can't see how far this extends up, but it's clearly going to have a higher positive y-intercept, and it does go down 4 and over 1. So this next graph, here's another example. This is our typical, we'll call this k of x, is going to be equal to our x cubed. But again, if I want to find my inverse, I can, again, switch the x and y. So x is equal to y cubed. And then we're going to go on from there to find, solving both sides for y, we find that y is equal to the cubed root of x. And believe it or not, that's actually the graph. The green there is the graph of y is equal to x, the cube root of x. And then I also put the blue y is equal to x line. So you can see again that they're mirrored. So the purpose of this one is what happens if I have like this, something like this. So let's say I had y is equal to 10 to the x. So I know that, actually I'm going to put that in black because I want that to be consistent. So let's say my original was, let's say t of x is equal to 10 to the x. Well, I know that when I'm finding my inverse, we are going to, again, switch the x and y. So we have x is equal 10 to the y. And think about it for a second. How would I get y by itself? How would I pull it down from that exponent? And the answer is, so far, up until this point, we don't have a resource for that. And so what that brings in is the advent of logarithms. So the answer to that is basically log base 10, or that's our common log, of my y, of my x, goodness gracious, of my x is equal to my y. So what we're going to be learning further on in this chapter is how to deal with these, the rules of logs as they relate to the rules of exponents, and then switching between the different formats. So the whole purpose, again, is finding the inverse, seeing what it looks like on the graph, and then understanding that basically what we're doing from here on out is finding the inverse of our exponential graphs.